Okay, I think we can get started. So the idea of this session and several others that will follow is that we do some sort of live coding, loosely speaking, because at least in the first one here, we're not actually coding, but we're using code. And then in some other ones, we'll actually do a little bit of coding. Now, as I mentioned yesterday, we know there's a huge diversity in your background. So for some, this is the first time you're playing around with R and those kind of models. Others are already pretty proficient in coding. So if you're one of those who, you feel this is going too slow, feel free to jump into any of the other apps or start looking under the hood earlier than we all do. And then, if you have questions, definitely ask them. And I don't have a problem having side conversations with people that are more advanced, but I want to make sure we start at the beginning for those that sort of need a gentle introduction. And I have all the Zoom hopefully set up right here that I can see the chat, but I can't also monitor Slack at the same time. You can still post it there, and Cody might answer it, or Paul, or they might transfer it over to the chat where I can see it. And of course, also, feel free to unmute yourself and ask a question as we're going. So in the first session, I figured we'll do the basic approach, which is just using it through the graphical interface. So you can get an idea of the, just playing with the models and the overall setup. And then in further sessions, we'll start going a bit deeper and starting to first touch the code a bit and then actually look inside these functions. So I figured the first one we can start with. And the idea is you as I do it here, you do it at the same time on your own setup. And I might just, sometimes say, okay, now take the next 5 minutes to do it. And then I'll give you a few minutes and then I'll catch up. So you can try it for yourself. So I hope everyone got to this stage here. Make sure you have this version here, 0.88. I just updated this one because we made some changes. The old versions work too, but mostly in the what to do part, documentation part is where we make updates. And we'll keep making updates. I hope by the end of this, we'll have them all updated to a new sort of structure. So once you got this, you have your main menu, and they're kind of sort of organized according, in some sense, topics and difficulties. So the idea is you first do the basics, definitely the basic bacteria model, and then it starts teaching different topics and gets more interesting. As I mentioned yesterday, I know there will be some of you that are interested in fitting these models to data. So those would be under model fitting topics. We don't have the time to really dig into that here in that short time. So I'm not gonna go into that unless there's specific requests that we should do that. But definitely feel free if you're interested to dig into those. Especially if you're feeling comfortable with these kind of models already somewhat. We'll start here at the first one today, the basic bacteria model. And so for all of them, you click on there. And so one thing you might have already caught or so is that, the thing is the way this is the back button that you would like to use to go back to the menu doesn't actually work. Just the way this kind of shiny app is written, you just otherwise have to click back to the menu to get where to all the ones. So we'll start here. And so then for each one, and they all look the same, you have the your inputs that you can change on the left side, then your results on the right side. It starts blank because we haven't run anything yet. And then underneath is really all the important part, the information. You see always these 4 tabs. The first one is very brief, just a very, one paragraph, what it's all about, and then some learning objectives. Then the 2 really important ones are the model and the what to do. The model gives a fairly detailed explanation of the underlying model, what's going on. Hopefully enough that, even if you're new to these kind of models, you kind of get the idea of what's going on here. So in this case, it tells you that there are 2 compartments or 2 variables or 2 entities that we're tracking here, bacteria and immune response. So we keep it very simple, just some nondescript immune response. We can think of it as either a certain component we're interested in, let's say just T cells, CD8 T cells, or you can think of it as the totality of the immune response, somehow defined. It's simple, it's abstract, but we can still start to explore it. And then underneath it describes what processes are implemented. So once we have these entities, we have to decide what mechanisms we want to account for. Again, the hallmark of our models, as I mentioned yesterday, is the fact that they have explicit mechanisms in them. So they're described here. And then below it, you see the diagram of the model. And that's a nice graphical representation showing you the compartments is always boxes, and then the different things that can happen here. In this case, these bacteria can die, they can grow, they can be killed by the immune response. In turn, the bacteria induce the immune response, and the immune response dies. These diagrams are very useful when you build your sort of first models, or anytime you build a model. It makes a good idea to sort of just scribble down a diagram and figure what goes where and what interacts with what. And then at some point, if you want to implement it on a computer, you have to put it in some kind of mathematical form. And the most common one is these ordinary differential equations. So that's a continuous time deterministic, meaning if you run it over and over again, you get the same answer. And so that's the one we'll use most here, because it's also the one that's the most widest used in research. You can write it equivalently. So this diagram doesn't quite specify it how you formulate it, and this description doesn't either. It just tells you what components and what they're doing. So here's an alternative way of writing it, a discrete time way of writing it. It's maybe initially easier to understand how things update in time, but discrete time models are not used quite that often. There are features that make ODE models more convenient and maybe also more realistic. And so we'll look at this here in the first one, but after that, in most of them, we'll focus on this. And then there's also the possibility to have this as a stochastic equivalent. So in these two models, we're having deterministic ones, meaning every time we run the model again, we get the same result. But real biological systems have always a certain amount of uncertainty and noise. And so if you want to incorporate that, you want to switch to stochastic models. And if you want to explore those more, you see here is stochastic dynamics. And I think this one is actually stochastic too. So there are a few models that have that component in there. So you can look into those, and we might not quite get to this, but if you start looking at it and have questions, we can discuss. And there's also in one of the lectures that is on the webpage, I talk about those a little bit. So that's the model part. So for every model you want to read this. Often models are reused. So, for instance, here we have this basic model, and then in the bacteria model exploration, I'm using the same model again to just do other things. So then I'm not describing it in that much detail. I'm just repeating here the diagram and the equation. So, sometimes the idea is you work through those first ones, and it usually tells you up there, I assume you worked through this. So it tells you which ones you should have done first before you jump into one to get the underlying model caught up with it. And then really to some extent, the meat of all of these is in the what to do. This is sort of a sometimes long, sometimes short list of tasks that I think if people work through those, they will learn what I'm trying to teach with the specific app. In this initial ones, it's just for getting to know those models and exploring them, and then in later it's specific topics. For instance, in the fitting one, the idea is by going through it, you will learn some of the basics of how fitting works. Of course, it can't replace a full course on those kind of topics. So it's if you wanted to learn it just using this software, you probably need to do a good bit of additional reading. And I've tried to provide some information here. So on the further information one, the two components that are important is it tells you what the underlying function is that's running the model. So we'll get to that soon. So you can actually call that directly instead of using the graphical interface. And that has advantages. You can have more flexibility. Of course, the disadvantage is now you have to start actually writing a little bit of R code. And then also, I often try to include some further reading for similar models or more learning about the topic. So that's in the further information section. So every app has that structure. There's different amounts of information in certain sections. So for now, the idea is we'll go through this one and see how far we get and play with it. And I'll let you play with it yourself. And, I'll just try sort of get the hang of it. So the idea is, here's the first app has a good bit of additional information. And one thing that I actually notice is challenging for people is the, how to convert things, biological quantities to parameters in the model. Sometimes there is not even a clear conversion. For instance, the rate at which uninfected cells infect virus. We really don't have a good, biological measure of that. It really only comes from these kind of estimates through models. But other quantities, have biological meaning, like, the lifespan of certain cells. Now that usually we measure it in days, we say, the average lifespan of a T cell is whatever it is, a month or something. But in these models, you need the inverse of that. You need rates, and you also need to make sure your units are right. So that's the thing that, when students don't get the right answer, it's often the conversion part. So it's just something you need to practice and be aware of, that, that you have to take the biological quantities and then make sure they match what you actually implemented in the model. Okay, so now I see the question in the chat. The question is if the interface is adequate for a complete workflow. I assume you mean, can you use this package to do actual research? The answer is no. This is really mostly meant as a teaching tool, especially when you go through the graphical interface. I hard coded these models underneath, and they are to be mostly simple, so you can learn the material. So in that sense, they're not flexible enough. Now there is the option, and we'll get there, and we'll do that tomorrow. You can download all the underlying simulation functions, and if you have a problem that is sort of, would be well described by one of these functions, you can use that as a starting point. Most likely, you will still have to modify it. So you will basically adjust it to your needs. Basically, what that means is for any kind of real research problem, you will likely have to actually do R coding. This interface here, just the graphical, is not enough for that. This is mostly meant to learn it and to teach it and sort of get a gentle introduction. If you want to sort of, become a modeler, then usually there's no way around in actually writing code. But some, if you use those kind of functions that are provided, it might make your life a little bit easier. So yes, expect this sort of as a starting point to learn it. And then at some point, you'll probably have to dig deeper and really delve into the R code. And hopefully we'll get to that by tomorrow, at least seeing it a little bit. Okay, so let's give it a try. So here there's always has the same structure. You see the task, and then in the new version, and we'll eventually switch them all to this, it tells you what you should record. Now, for our purpose, that's not that crucial. When I teach the course, full time with grades and all that, then, students actually have to put these numbers in a spreadsheet and that gets graded. We won't do that here, of course. But this is, the idea here is that you try it out and you play with it. So you don't always have to like scroll up and down, which is a little bit annoying. You have the option here to take all these tasks and just sort of put them in a floating task list here. So then what you can do is you can sort of, read here, and at the same time as you read through as you adjust over there. So that makes it a bit more convenient. If you find it's in the way because you can't see your figure, you can just remove it again. So that's might be useful. I often find it useful to have it there. So here it says, start with this and this and the other, and I'll basically let you read through it now, and I'll just give you a minute or two and, change those settings over there if they need to be changed, and then run the simulation and see if you get what it says you should be getting, just to make sure it works. So I'll just pause here for a minute or two and let you try it. So it turns out in this case, and I think in most other cases, that starting values I give are the ones I've already coded as the defaults in there. So, when you run the simulation here, you should see what it says you should see. So, 1900, 19,996 and 303. So you see that's here. So pretty much for every app, you will see some kind of plot here. Usually it's a plot of the time series. So you see the two or whatever number of compartments we track, in this case, the bacteria and the infected cells, as a function of time. Time in this case is we decided we run our model in days. The way you choose it is basically you have to choose the parameters in the right units. So here, if we decide that, they live for 2 days, and so their decay rate is 1/2, so 0.5 per day, that means we're running our model in days. You could also decide to just have express every parameter in some other unit, like weeks or months or minutes. You should choose something that, makes sense for your system. If you study an acute virus infection or something like this bacteria infection here, days tends to be a good unit. If you wanted to sort of study the long-term dynamics of HIV, you might want to switch to weeks or months or maybe even years. So it's basically whatever you think is the best unit. It doesn't matter. You can sort of recompute all parameters into different time units and things will be not changing. You just get different time units on your x-axis. But you just want to make sure you don't mix and match. You don't want to have one parameter expressed in days and another one is expressed in weeks. So you need to then adjust for that. And so you see here for those settings, what we have see bacteria grow initially, and then that leads to the immune response being activated and growing too. Then they're high enough that it leads to killing of bacteria. Then because the bacteria go down, it also leads to less immune response being induced. So they go down again, bacteria recover, immune response does it, and they do that in cycles. If you've seen something like that before, you might have seen it in ecology, the predator-prey model. So that's basically what we have here. The immune response is the predator and the bacteria is the prey. And so they do that for a while, and then they basically reach some kind of stalemate where the bacteria settle down at some level and the immune response settles down at another level. And so you see the figure here, and then underneath there's always some text output. It's not always the same. It depends on what kind of app you're looking at, what the output is, but it's usually something that could be useful. So in this case, it just gives you a few summary for the whole time series. The max of each of these variables, the minimum would be this, well, in this case, actually here at the front, the minimum, and then the final value at the end. If you look over there, you have different ways you can play with it with the output. You can, for instance, change the scales. Unfortunately, it's set up such that you always have to rerun your simulation, which one doesn't really need to because the underlying model doesn't change. It's just the way I've coded it here. So here is on a log scale. Sometimes one scale is better than the other. In this case, I'm not sure which one is better, but sometimes one scale really tells you more. And you could also do the x-axis on a log scale. However, there's rarely much sense in our kind of models to have time on a log scale. So that's just in there, so you could do it, but I think most of the time you don't really want to do this. So either it's the y-axis or no log scale. And then it also allows to use Plotly, which is just another package in R that makes plots. So ggplot is sort of the most commonly used one. It makes very nice plots, also very good plots if you need figures for papers. The nice thing about Plotly is that it's interactive. So when you run it, you see it here. And the nice thing is here, you see I move over with the mouse and I can actually read off the numbers on the whole time series. And I can, for instance, turn off one of those. It could be useful if you have a lot of different variables that you track, like 10 or 15, and you don't want them all in there. You could turn certain on and off. And then, there's also, you can zoom in. So if you want to really see what's going on in this part here, you can zoom in. So that's a nice feature about Plotly. It lets you do some things like that. Most of the time, it doesn't matter which ones you use. Sometimes there's a question that says, read off the, time of the peak here. So you would then use Plotly, and it will tell you here that the peak is around 25, day 25. So that's harder to do with ggplot. So that's the first part we did here. And we already did that. We played around with the plot settings and changed the scales. And we looked at here the first peak, but we could look at the second peak as well. It's hard to read off here, but with Plotly you can do it. You just click on it. Any questions on this so far? I hope it's intuitive enough and people can get it to work. So one thing you have here, and a lot of other apps don't have that, but underlying, you can run either the ODE model or the discrete time model. So this is running the discrete time model, or you can run them both. So here you see them both. And what you see here is that they're very similar. And so what generally happens if you have a pretty small time step, then your discrete model is an approximation of the ODE model. In fact, while the ODE mathematically has sort of an infinitesimal time step, in reality, when you run it in the computer, you still have to take finite time steps. The computer just has a smart way of taking those time steps. So if you run a discrete time model with small time steps or an ODE model, you get pretty much the same answers. That's not the case anymore when you change the time step. So when you change the time step here, for the ODE model, it really only makes a difference in the points that are returned to make your plot. The underlying time step in the ODE model is not affected by that. But for the discrete time model, it actually does make a difference. So if we increase the time step here, they're starting to diverge somewhat. So you see there's now already a bit of a difference between the discrete time and the ODE time. And as you keep increasing the time step, you'll see that things are getting more and more different. And at some point, you might hit a time step that's so big that it doesn't make sense anymore, and your model might break. Okay, that one still kind of worked. I'm not sure where exactly it breaks. Okay, that one failed. You might see that occasionally. Also, if you put in crazy values for these parameters, it means you're trying to run a model for settings that just don't make sense. And then, you get this kind of error message here. Now, as I mentioned, discrete time models are actually not that commonly used for these kind of compartmental models. Most of the time we use ODE models. However, there's an area where pretty much every model is a discrete time model. And this is when you run individual or agent-based models, because you have to take finite time steps and you can't actually take really teeny tiny time steps like you would for an ODE model, because otherwise it would just take way too long to run your model. So you're trying to pick the biggest time step you can get away with. And basically, get away with means, you're hoping by making an approximation of just updating your simulation every day, you're not making too much of an approximation and jumping over too much that might have happened that you should have tracked. Or for a within host model, you would maybe update every hour. So you say every hour an infected cells produces so many new virus particles. And then you update in those time steps. But for those models, the time step matters. So you will have to explore that when you change the time step, your results don't change, because it's just an approximation. So your underlying system runs in continuous time. So your computer model your result should not be affected by the time step you choose, because it's sort of an artifact of your model. But these ODE or compartmental models, this is not that important a point. Or it doesn't show up that often. Not discrete models aren't used that much. Okay, so this was playing around with the discrete models. We've played out, we already saw it. We were able to crash it with that error message. And so, the real thing, what you want to do with those models, it was just sort of warm up, but, let's just switch to the OD alone. The reason why you want to build a model is you want to ask, how do certain inputs affect certain outputs? And you define what the outputs are, the measures of interest. So for instance, it could be, the B cells at steady state, or the peak of the bacteria, or the level of the immune response, whatever your question of interest is, the quantity you might be interested, or the number of T cells after the vaccine is given, or anything of that sort. So that's your outcome of interest. It could be just one thing, or it could be multiple things. And then of course you are asking, okay, how is that affected by other things, like the initial number of bacteria that are started with, or the rate at which they grow, things like that. So once you kind of know what you want to ask, how does X impact Y, then you're building your model that includes those features and other things you think is important about your system. And then once you have the model, you can explore it. So for instance, here we could say, okay, we have this steady state of bacteria and immune response, and we're curious to see how the number of initial bacteria that start the infection impact this. So we can run the model, instead of 100 bacteria, now we only have 10 bacteria starting the infection. Looks like it doesn't change it a whole lot. And in fact, if you run it for longer, I'll change T final here so we run it out further. We get 20,000 here, and you see if you increase it, it's actually the same. And we increase it tenfold more. So it turns out no matter what you start with here with the bacteria, eventually they'll always settle to the same number that's independent of the starting number. That might not be something that is obvious to you if you've never played with those kind of models. If you're familiar with that models, you kind of know that the initial conditions don't really matter much, but most of the time at least, but it might be surprising. And we could play around with the immune response and see if that's the same. So we change the immune response, and we see at the final value here, doesn't actually change much. So that's the kind of exploration you can do. And then you can say, well, let's now explore how, let's say, the growth rate of the bacteria impacts the outcome. Let's just do some sort of guessing or so. If we double the growth rate, what do people think the final state of the bacteria and the immune response is, without running it? Just, and I know if you've never seen these kind of models, it's really hard to intuit. And even if you've seen models like this and you get a slight variant of it, it might not be clear that you can say it. Does anyone want to venture without running it?
We might have a peak earlier than expected.
Yeah, so we might get something going up earlier. That's quite probable. What about here at the end? Someone that says no difference? I think if I had never seen this model before, I would say that if you increase the growth rate of the bacteria, then the number of bacteria at the end would be higher. That would be my, very naive thinking if it was the first time I had ever played with, and I would not be able to say anything about the immune response. At least that's what I would think, but one can see what happens. So it turns out the bacteria don't actually change, and the immune response did change. So let's compare again. So maybe somewhat surprising, as we change the growth rate of the bacteria, the number of bacteria doesn't change, but the maximum value of the immune response actually goes up. So, the point here is that, even this fairly simple model, just two equations, might produce things that are not easy to predict. And, we really need those kind of models to explore what a system would be doing. And so, of course, you can now explore that for a whole lot of other things. And here, for this system, it's simple enough that you can actually do some math and really compute this end state, which is often called a steady state. So you can compute what you would expect just based on the parameters. And so you you will see here that, here's the equation for B at the end. So you can read off from that it is independent of the growth rate. It just depends on actually the death rate of the immune response and the activation rate. And then here's a similar one for the immune response at the end state. It's a bit more complex, and you see there's G in there. So it does depend on the growth rate. Sometimes you can do that kind of math, but it really only works for the simplest problems and the simplest models. As soon as your model gets even moderately complex, meaning like more than 5 quantities you're tracking, you usually can't do that kind of math anymore, but you can always implement it and simulate it. And this is then, you build it, you run it, you explore it, and this is how you build intuition of what goes on in the system. Remember the example I showed yesterday briefly that I didn't show the underlying model, but I showed that figure for a TB model where in the model they depleted IL-10 or IL-4. So, in our simple model, it would be something like saying, we somehow depleted the immune response. We were able to, maybe we give a drug that leads to faster immune response decay, something like that. It's not a good equivalent, but, then you could see, okay, what would this do? In this case, it's a bad idea. Bacteria take off when the immune response is gone. But those are the kind of things you can then explore, right? You have some kind of biological question, and you see can I map that into my model? If I say, okay, no, I'm gonna give a drug that increases the death rate of the bacteria, that sort of helps kill bacteria. So you say, okay, the natural death rate is 0.5, and now I have a death rate of 1. So that's what it's doing. And then you can see what it does. In this case, they're just going down, so that is actually would be pretty good, right? We don't get any peak of the bacteria. So that's how you can map, your questions into a model once you've built the model and explore it. And through something like this graphical interface or the equivalent where you, change one thing at a time, it's, one way you can do it. It's convenient through that graphical interface, but at some point it gets a bit more tedious and you want to do it a bit more rigorous. And so we'll move to another app where I've sort of pre-coded that, where we can do that. Let's see if there's anything else in here. There's one other point that this app here makes, and we've seen that earlier before. It's hard to see here, but if we switch to a log y-axis, you can see the immune response drops to fractional values. And you will find instances where the bacteria might do that too. And that might not be very reasonable, right? Especially if you think of immune response, if we measure that in some vague units, the totality of the immune response, maybe it's okay that to be fractional. But if you assume the immune response is T cells or some kind of cell, it can't be less than 1. And also it can't be any fraction, right? We can't really have 3,003.48 or 19,000.01 at the end, right? We can only have total numbers. It's one of those sort of approximation that these sort of ODE models make, that your variable can take any value, including values lower than 1. Sometimes it's an okay approximation. If the numbers are large enough, 19,996 is basically the same as 0.01. You can ignore this. So you can say, yeah, this is good enough. And often that's justified. But if you want to study something where really low numbers matter, so often at the start or the end, then maybe these kind of models are not ideal. That's just something to keep in mind. And when either we or you by yourself go to the stochastic models, that will be discussed there in somewhat detail. There's a hand raised. Is there a question?
Yeah, hi. I think kind of you touched that. My question was about immune response. And what does it translate into? Like, is it like some time horizon, the parameter we are putting in the model, or like this is something like strength of immune response? How one can capture that?
You mean the I quantity?
Yeah.
Yeah, so you can think of it in different ways. You can think of it as either the total strength of the immune response, however you want to define it. Like you add up all the B cells and T cells and cytokines and everything and track it that. I don't know if that makes much sense because it's like adding up apples and oranges. Or you could say, okay, for this specific system, I know that the most important component of the immune response are whatever, NK cells or neutrophils. So I've seen a model like that where bacteria is staph and the I would be the NK cells or the neutrophils. So then you could say, okay, this is what I think. But basically, you would need to map for your specific system the biology to the model. And maybe there's a system where it's okay to only track one variable of the immune response. Quite often you might say, no, I actually have to track multiple. The next step, what people often do is they have one variable for the innate response, and loosely speaking, sort of, and then they might map that onto something specific. Let's say for flu, we know the interferon response is really important. So we say, okay, the innate response in my model is represented by the interferon response in the real system. But that's always sort of the challenge on how do you map something from the real system to a quantity in the model. So that's when you're starting to build your model, you have to decide, okay, I know in my system, these are the really important components, so I need them in my model. And if you know I need this in my model, then you give it an equation. Now there's sort of anyone who's sort of in the hard sciences trained tries to start very small and just adds more details if it's absolutely necessary. And most people that are bench science try to throw everything in there, start with a huge model with 50 variables, and quite likely the sweet spot is somewhere in between. You need a certain amount of complexity to get a decent approximation, but you can't just include everything. And so if you remember some of the slides Paul said showed where everything signals to everything else, and there are all these cytokines and receptors and things, there's usually no point in including all of that in the model because we just don't know enough about it to actually write down reasonable mechanisms by how they talk to each other. So often what you do is you say, okay, let me pick the one that I think is the most important or that I'm most interested in, put that in my model, and either completely ignore the others or lump them together in just one other compartment that I call the innate response or something like that. Unfortunately, there's no recipe. That's really where the art of modeling comes in. You need to know enough about the science that you can make a model that hopefully makes sense.
Well, thank you so much for that. And like a follow-up question, you can like ignore for now if you're planning to cover it later. Like immune response is quite like a dynamic process, and somewhere it would change, like talking about vaccine or something like that. So is there some way like we can consider that as part
well,
of
you see here in our figure that the immune response is dynamic, right? It goes up, then it comes down. So that's why we're giving it a variable, and then we're running it, so we allow it to go up and down again. So
Thank you. Yeah.
Okay, let me look at the other ones in the chat. Suggests that the immune response killing bacteria too quickly could be a bad thing in this model. This is a very simple model. So if you have a real world system where you think this simple model actually applies, then maybe that's a reasonable assumption, but that's sort of a scientific conclusion judgment call you need to make to say, is that model a good enough approximation? One sort of related one where I've seen that recently is we built a model where we had for flu, we're fitting data for flu vaccines, and there was the innate response and the adaptive response in the model. And of course, for the vaccine, you want adaptive response to be induced because that's what stays around and protects you. And we saw that, under certain situations, it could be that the innate response kicked in so fast and cleared all the antigen in the vaccine quickly enough that the adaptive response didn't even have time to come in. So in this case, having an immune response that is too good, at least an innate one, prevented the adaptive response from, actually building up. So it is somewhat related. So I think, yes, it could actually happen that sometimes, especially if you're thinking about, inducing the adaptive immune response, you want to make sure that it actually gets triggered. And if the innate response can take care of it quick enough, then you will never actually trigger it. Another one is why some simulations model done with a log number. I mean, right here, we're just doing it for the final plot. So the underlying simulations were not running anything in a log space. We're just looking at it in the plot in the end. And basically, you always want to pick the plot that, is most, meaningful. I'm just going to flip real quick to another app. Let's say we go to this one. The details don't matter, but basically you have your data on model and you see this is not very insightful because all the data is sitting down there and the model is sitting on top of it because, this high U just clobbers everything. So in this scale, just, plotting it on a log scale, is now much more meaningful, can actually see the data and the model closer to each other. So most of the time you're, for the plots, just what makes it easier to see what you're interested in. Running the underlying models in log space, I can't think of an example right now where that would make sense. You might have in your processes, for instance, if we looked at the model here, here we are assuming that, the immune response is proportional to the bacteria at some rate R. That's how it's induced. There are sometimes models where people assume that the immune response is sort of senses the pathogen not on a linear, but on a log scale. So you would write this R times log B times I. That could be reasonable and kind of depends on what you think, how, in this case, in this example, the immune response would be triggered. So sometimes in those processes, you might see logs, but the variables itself, they usually just run in whatever sort of natural units or experimental units. If you want to match it to an experiment, then your B would be in, plaque forming units. If you had, for instance, bacteria there, and the immune response would be whatever you're measuring in your system. Let's see what other questions is here. Bacteria growth rate to 0.7. Got odd results. Let's see that. So basically, just suggests the bacteria grows at a rate that the immune response isn't really induced much and then goes away. I don't know if that's the same result that you got or not.
No, I actually got a different result. I don't know if it's my plot is just wrong, but when I did the growth rate equals 0.6, it made sense. 0.8, it made sense, but 0.7, I don't know. It just got all weird. I don't know. Maybe I have an old version or something. But
I don't know. What's it showing?
It's just like a flat line. I can try to do like a screenshot maybe, but maybe there's a different value.
Usually if 0.6 and 0.8 work, then biologically the intermediate one should kind of work too.
Right, that's what I was thinking.
not sure what's going on. Yeah.
Let me see if I can post it. Maybe I did like some other input that was different. Let's see.
Yeah, you can just hit the reset input and then.
Yeah. All right. Well, I attached the photo to the chat of what mine looked like when I ran it. I don't know if other people got that or if I'm the only one. If it's just me, that's fine.
Not sure how to open that. Basically nothing.
Yeah. I think all my inputs matched. But yeah.
I don't know. Yeah, surprising. Oh, your time step is different.
That shouldn't cause that much of a difference, would it?
No, but
Maybe.
it looks like, but that might be an indication that you're not running the current version.
Okay.
Does your what to do look like this with these record thingies?
Oh. No.
Then you're having the old version.
Okay.
There's minor tweaks under the hood that have gone on.
Got it.
Now, I don't know why it should look like this in the old version. It shouldn't really, but yeah, I'm not sure.
I think you had DVT of 0.05. And
yeah, that was one thing in the previous one.
Yeah.
So there's one slight sort of thing I jumped over. I said the time step doesn't actually affect what the ODE solver runs with. It's only where it returns the plot. That is mostly true. However, if you feed the ODE solver certain time steps for which you say, I want it back for that, then it makes sure it actually hits those time points. If you don't give it those, it might actually make bigger jumps than you want it to make. So if I say it, I only want it for 0, actually, let me try it. What happens if I do this here? No, doesn't do it. So sometimes the ODE solver might just make jumps that are too big if you don't tell it to want it fine grained. So even though in theory the solver picks its time step, if you say I want it definitely for these times, then you kind of force it to stop at those times instead of taking even bigger steps. So that's sometimes can affect things a little bit. But yeah, that gets sort of a bit nitty gritty. That's why I was kind of skipping over that.
Dr. Handel, I have a question. So for the plot right now, the line of immune response seem to be truncated. What does that mean? Like, is that 0?
So what it does, you actually see here the minimum value is 1.7 times 10 to the minus 21.
Oh, that makes sense. Yeah.
So you start somewhere and that it can't get negative. Well, actually, sometimes numerically it will get negative, even though it's not supposed to. But it starts somewhere and it approaches 0. It gets closer and closer to 0. And so basically in the plot, there's just I think the cutoff is like 10 to the minus 20. So what it does, the line actually goes below that and it's basically kind of gone. But, you basically can interpret that. And in this case, when we plot it on the y-axis, this might be, yeah, here you kind of see it, it just goes very far low and then kind of slowly comes back up again. So it's just the truncation of the plot.
Okay, thanks. Also, I'm playing with this. This is pretty fun because we can have many different results. So I'm trying to find this to simulate like we could eliminate all the the pathogens, but I can't really find a way.
To eliminate the pathogen?
Yeah, like.
Well, we did one, right? If we had here the bacteria death rate, if we said it would die even faster at 1.
Oh.
It's basically it starts at 100 and it's declining, so it will never grow. So if we let it run for longer, we'll just probably keep going down.
Okay,
yeah.
Thanks.
So if we make it even more extreme, the killing, yeah, now they're both gone, right? So yeah, so this is one way you can eliminate it. Anything else? Any other questions on? I haven't checked Slack. Let me look at there. Not seeing any there in the modeling related. Okay, then we're running until what time again? I think 2 my time, 11 Seattle. So I've got 20 more minutes. Someone correct me if I'm wrong. So let's spend the last few minutes looking at another one in sort of this graphical interface. And then in our next session, we'll move away from the graphical interface a little bit and, go a step further in actually playing with the code. There's a question, does the ODE always have an exact solution? I'm not sure, do you mean by exact like a mathematical one that one can compute, or always the same answer, or?
Yes, I mean one that you can compute.
No. So even for this simple model, why we can write down something here for the steady state, for the state at the end, for this one, even for this simple model, there's no exact solution, let's say, for the maximum, meaning analytic just in terms of math. And as soon as your model gets bigger, it gets even more impossible. So most of the time, no, you don't get very far with math. That's why almost always, you have to put them implemented in some kind of computer language and simulate them to explore it, because there's, you can't do it. Will repetitive runs bring similar results? Yes. You see, I can hit this here as many times as I want. I always get the same result. And that's that feature of the fact that this is deterministic, meaning there's no uncertainty in this model. It's always, once you specify your starting values and your parameters, it doesn't matter how often you run it, always the same. The only way you can change results is if you, excuse me, if you change your parameters around or start at different values. No, that's different than when we go to later ones, like the one with the stochastic dynamics, where the underlying process allows for some kind of randomness. So then you run it multiple times, and each time it looks different. But for these kind of models, the ODE-based models, it's always the same. Okay, let's briefly then, but keep the questions coming as I see them, I'll answer them. We'll briefly hop to the bacteria model exploration, and this is exactly the same model, and it's kind of the same idea, just now instead of manually having to change a parameter around and change it for b equals 2 and then b equals 3 and changing the values manually, this gives you a little bit of automation. And this is sort of these kind of plots that we'll now produce are some that you will often actually see in publications. So it's the same model again. So you have the same parameters. What's now new is that you have here something called samples and a min and a max and a parameter to vary. So what it basically does, that instead of you having to manually put 10 different values for that parameter G in here, the underlying code just runs the model, in this case 10 times, because you have 10 samples for values of G between 2 and 10, and then it gives you the result. Now, in this case, underlying it produced this 10 time series, but it's not showing you all 10 time series. Instead, it just takes the time series, which is basically the complete solution. Then it computes from that these things you've seen at the bottom, the max and the final state, and the min, I think too. We'll see what it does, and gives it to you. So just the peak and the steady one. So basically, conceptually, it runs this model for each value of the parameter. In this case, the parameter G here. This one here, it goes in, it reads off the maximum here, and the final one, it saves it. It runs the model again for another value of the parameter G. It reads off the maximum and the final value again, saves it, and keeps that doing for the number of steps you wanted to do it. So, in this case, 10, and then gives you a plot. And so basically this now, let's say you had a scientific question where you wanted to know the steady state of the bacteria and the immune response. How does that vary with the growth rate of the bacteria? So that would be your answer to this scientific question, right? Assuming that this model is a decent representation of your underlying biological system, this could be a real, the kind of figure you see in modeling papers, where they have a model, they vary some quantity of interest and look at some other quantity of interest here at the outcome. So that's basically what this app lets you do. And then, you can say, well, I need a bit of finer resolution. This just runs it at more time points. So you get, more details. Of course, it takes not twice as long because we're running the model twice as many times. You could say, well, I actually want to start at 1 and I want to go to 20 with that parameter G. Usually you have some ranges in mind that make sense, usually based on biology. For instance, max growth rate of bacteria. We kind of know that the fastest time a certain bacteria can double. If you had E. coli, you know that, maybe their fastest way of doubling is every 20 minutes or something like that. So then you might, choose that as your upper value of your G. You have to convert it, of course, in units per day in rates. And then you could say, well, if I had very lazy bacteria, this is the lowest they would replicate. And then you choose that as the lower value. And here now it lets you pick other parameters. So for instance, we could do Bmax, which is the carrying capacity. Now Bmax between 1 and 10 doesn't make too much sense. And I think the outcome will be not very meaningful. Yeah, there's the carrying capacity now is so low that the bacteria here be steady just can't reach much. It's pretty low. But let's say we set carrying capacity between 10 to the 4 and 10 to the 7. Now you see that's a pretty long range. So now if we said we want them linearly spaced, the parameters, most of them would actually be at the upper end. So let's just run it to see that. And depending on the values, it can take longer for the simulation to run. And if you choose really crazy ones, it might fail. So that can happen too. Then you'll get an error message saying, this didn't work or something like that. Now, apparently for this one, I've chosen values that make it run pretty slow. Okay. So you see now here, 0 is just kind of, it's just because we're having here a linear scale. Almost all points are between 10 to the 6 and 10 to the 7. What we usually want, if we have a parameter that spans many, orders of magnitude, we want to sort of uniformly scan it on a log scale. So we want to say we scan it on a log scale, and then also it's probably best if we plot it on a log scale. So that's one example where we want to have the x-axis on a log scale, because we don't have time right now here on our x-axis. Now it's going to take a while again, but then we can see how things look like on that scale. Okay, now here we're looking at on a log scale. So, you see from 10 to the 4 to 10 to the 7 logarithmically spaced values, and you see there's, decent sort of curve for those steady ones. You see the peak ones are a little bit actually crazy here. They jump up and they go down again. I think what's probably happening is that the time step isn't detailed enough, and then it, just sort of tries to read off the optimum, but it only has this much, the time series is not very fine. So if we make this finer, of course, the problem is now it will take even longer to run. So we'll see what happens. But I'm thinking now it should maybe not look so weird jagged around here. There's a request when we interact with the code and we can make adjustments, parameter spacing. Yeah, we'll look at that. That's actually a setting in the code. Did it run? That didn't do much. Oh, okay. No, I made a mistake thinking here. The problems are actually the steady ones here, B steady and I steady, that are jumpy. And this here is kind of a warning message. So, we're running the underlying time series. The steady state only makes sense to sort of read off at the end if it's actually settled down. Now here we're not actually seeing it. If we saw the plot, and it's always good to look at the plots, we could see, has the system actually settled down? If it hasn't settled down, it's kind of doesn't make sense to call that the steady state. So it tells us here that it hasn't reached the steady state 9 times. So that means some of them are actually not, just by chance are still up. So to ensure, help it reach the steady state, we'll just have to run the simulation longer. Of course, the drawback for each one of those is that it will take longer. But let's see what it does, if that helps smooth it out. So always consistency check. Whenever you see results that look weird, it's rarely the software's fault. So, it's quite often if the software does something weird, it's because the user asked it to do something weird. So, it's always good to very carefully see what's going on. You see it's changed, but it still hasn't quite fixed, and it still says 8 times not settled. So let's see how patient we can be and how far we can push it out. And if that gets us there. In the meantime, any other questions? And of course, here now you have the What to Do app again, which has a bunch of tasks that sort of work you through those steps and explore this idea a bit more. But that is, it's getting better, but still not there. I'm out of patience now. I'm not going to run it even longer. You see, we're still 6 times that we haven't reached steady state. But it's very simple, but this is sort of mimics real world problems, how, you would use models. You have some outcome that you're interested in, some input you're interested in, you build a model, you scan over that range of inputs, and sometimes it's just a single parameter, sometimes it might be a combination of parameters. And, you could here take it one step further and loop over 2 parameters, and maybe we'll do that later today. Remind me to do that. And then you could do something like a heat map, a 2D plot. Of course, as soon as we go beyond 2, we can't really plot it anymore easily. But you can explore as many inputs as you want. Often you have one or a few that these are my main interests. And then, you also usually have some outcomes that you're interested in. Sometimes either just a single one, the level of antibodies following infection or vaccination or something like that, or the steady state value of the bacteria or something. But sometimes you might have more than one. And then you build those models and explore them in this form. And so again, here, every time it tells you the underlying functions. So in this case, this is sort of this is a basic function here that runs the underlying model. And that is basically the function that does the repeated calling for different parameter values. So it calls the underlying one for multiple for parameter values, gets back what this one reports, saves the peak and the steady state, then calls it again for a different value of the parameter and keeps doing that, and then eventually gives you back the whole sort of scan of the whole range that you asked for. So what we'll do in the next modeling session is we'll actually start directly interacting with those functions. And then I think tomorrow we'll actually peek inside those functions. But just sort of a sneak peek, you can download all these functions if you click on the download R code for simulations. And pull one over real quick. So here's the basic bacteria ODE. And so it might look intimidating to those that have never coded, but that's actually the whole model here, the whole function. And so if you look there here, you might see these kind of things that we saw in equations just now written in code. And that's the thing that is run underneath, that runs the model and gives you the answers. And so, of course, at some point you could take that and change it any which way you want. You could include a second bacterial compartment here, but then you would have to start, coding around. And hopefully we'll get a little bit to that tomorrow. And this also here in this help file up there, it always tells you how you can actually call that function directly without the graphical interface. And so we'll play with that a bit later today.